we will discuss about equilibrium constant. So first we discuss about the active mass. Active mass. So what is active? So we can say this as effective mass, active mass or effective mass. And what is active mass? Active mass is a molar concentration. It is a molar concentration which is represented by this, and which is equal to the moles by volume in liter, and we can represent moles by volume in liter as the weight by molecular weight into the volume in liter, and we can also represent as this weight by volume is density, which is represented by rho by molecular weight, and here the density is in gram per liter. Gram per liter. Then the question arises that why it is known as active mass or effective mass. So for this we take an example. We take three containers. In this container we take 32 gram of oxygen, and in this container also we take 32 gram of oxygen, and in this container also we take 32 gram of oxygen, and here the volume we take is 1 liter. Here we take volume as 2 liter and volume 3 liter. So first we find the molarity, and we know that molarity is moles by the volume in liter. So here it is moles is 32 by 32 by the volume, which is 1. So it is 1 m. And here the molarity is 32 by 32 and the volume 2 liter, which is 1 by 2, means 0.5 m. And here the molarity is 32 by 32 and the volume 3, 1 by 3, 0.33 m. So the rate of reaction or the activity of molecule is highest in this container due to concentration. Now we take other example. In this also we take three containers. In this container we take 32 gram of oxygen, and in this container we take 48 gram of oxygen, and in this container we take 64 gram of oxygen, and we take volume. Here it is 1 liter. Here also we take the volume as 1 liter, and here also the volume is 1 liter. So first we find the molarity. So here molarity is 32 by 32 by the volume 1 liter, which is 1 m, and here it is 48 by 32 by volume 1 liter, which is 1.5 m, and here it is 64 by 32 by the volume 1 liter, which is 2 m. So here the rate of reaction or the activity of molecule is highest in this container due to concentration. So we have observed that the reactivity is not decided by only volume or only by amount. It is decided by the ratio, which is the moles by volume in liter. It is the ratio moles by volume in liter. So now we talk about the active mass of solid and pure liquid. So active mass of solid and pure liquid is considered as 1 because the density or the concentration and molecular weight are constant of the solid and the pure liquid. So it is considered as 1. So now we talk about the law of mass action. Law of mass action. So law of mass action was given by Gullberg and Varghese. It was given by Gullberg and Varghese. And according to law of mass action, the rate of reaction is directly proportional to the multiplication of concentration of reacting species, and it is also directly proportional to the partial pressure of a reacting species, and it is also directly proportional to the mole fraction of a reacting species. So for this we take reaction when A react with B, so this forms C and D, and initially at t is equals to 0 we take this as A, and they are not formed. So at any time this will be A minus X, and X and X. And as we have discussed that the rate of forward reaction is directly proportional to the multiplication of concentration of reacting species, which is A and B, and the rate of backward reaction is directly proportional to C and D. So if we remove the proportional sign from here, so this will be rate of forward reaction is equal to Kf A and B, and this Kf is the forward rate constant. And if we remove the proportional directional sign from here, so the rate of backward reaction will be equal to Kb C and D, and this Kb is the backward rate constant. So now we discuss about the equilibrium constant. So according to equilibrium, we know that at equilibrium the rate of forward reaction is equals to rate of backward reaction. So here it will be Kf forward rate constant multiplied by A, B will be equal to the backward rate constant multiplied by C and D, and this will be the forward rate constant by the backward rate constant is equals to C D by A and B, and this is known as equilibrium constant. Equilibrium constant is represented by K. So we can define equilibrium constant as the ratio of forward rate constant to the ratio of backward rate constant, or the ratio of the multiplication of concentration of product species to multiplication of concentration of reacting species. So this equilibrium constant, is a physical quantity. Which varies with temperature. It is a physical quantity which changes or varies with temperature. So now we talk about the forms of equilibrium constant. So if you have to represent by concentration, so we use Kc. By partial pressure we use Kp, and we represent by Kx also. So the Kc will be equal to multiplication of C D by A and B, and the Kp will be equal to the partial pressure of C into partial pressure of D by the partial pressure of A into partial pressure of B, and the Kx will be equal to the mole fraction of C into mole fraction of D by mole fraction of A into mole fraction of B, and this Kp is only for the gaseous species. This is only for gaseous species, and the Kx and the Kc is for both solution and for gaseous species. So now we talk about the relation between Kp and Kc. So for this we take a reaction when N1A react with N2B, so this forms M1C plus M2D. So we know that at equilibrium the rate of forward reaction is equals to rate of backward reaction, and the concentration of reactant and product are constant, and these two properties define a new quantity which is the equilibrium constant. So here the Kc will be equal to C to the power m1 d to the power m2 by a to the power n1 and b to the power n2, and the Kp will be equal to the partial pressure of C to the power m1 into partial pressure of d to the power m2 by the partial pressure of A to the power n1 into partial pressure of B to the power n2. And if we talk this for the gaseous species, like we take a container, and this we take gaseous species like A, B, C, D, and we combine this. So we know that for ideal gas we use the equation PV is equals to nRT or P is equals to CRT. And if we write that the partial pressure of A, so this will be ART. For B, so it will be BRT as this. So the Kp will be equal to the CRT to the power m1. This will be BRT to the power m2 by ART to the power n1, and this will be BRT to the power n2, and we can write this as that Kp is equals to, here it will be C to the power m1 d to the power m2 by a to the power n1 and b to the power n2, and in this the RT is common, so RT to the power, this will be m1 plus m2 minus n1 plus n2, and this is the delta Ng. Delta Ng is equals to the sum of stoichiometric coefficient of product minus sum of stoichiometric coefficient of reactant, and we can write this as that Kp is equals to Kc RT to the power delta Ng. So now we discuss the relation between the Kp and Kc. So if this delta Ng, if in the first case we take, if delta Ng is positive, then Kp is greater than Kc, or the Kp by Kc is greater than 1, or Kp minus Kc is greater than 0. And the example is the dissociation of PCl5. PCl5 into PCl3 plus Cl2. So here the stoichiometric coefficient is 1 and 1, and at the reactant side it is also 1. So the delta Ng will be equal to 1 plus 1, and this will be minus 1. So which is 2 minus 1, which is 1. So here the delta Ng is positive. Then the second is when the delta Ng is negative, then the Kc is greater than Kp, or we can say Kc by Kp is greater than 1, and we can write as Kc minus Kp is greater than 0. And the example is the formation of ammonia. When nitrogen reacts with 3 moles of hydrogen, this forms 2 moles of ammonia. So here the stoichiometric coefficient is 1, 3 and 2. So the delta Ng will be equal to 2 minus, this will be 4, which is minus 2. So the delta Ng is negative. And the third case is when the delta Ng is equals to 0, then the Kp is equals to Kc, or we can say that Kp by Kc is equals to 1, or Kp minus Kc is equals to 0. And the example is when nitrogen reacts with oxygen, so this form 2NO. So here the stoichiometric coefficient delta Ng is equals to, stoichiometric coefficient is 2, and here it is 1 and 1. So 2 minus 2, which is 0. That means that delta Ng is equals to 0, where Kp is equals to Kc. And the fourth case is if the RT is equals to 1 or T is equals to 1 by R, and this 1 by R value is, means the temperature is 12.18 Kelvin. So at this temperature, Kp will be equal to Kc. Kp will be equal to Kc for all the equilibrium. And when the delta Ng is equals to 0, then the Kp is equals to Kc, and this is for all temperature. This is for all temperature, and this is for all equilibrium when Kp is equals to Kc at this temperature. So now we talk about the units of Kp, Kc and Kx. So the unit of Kc is mole per liter to the power delta Ng, and of Kp it is atmosphere by delta Ng, and Kx is unit length. It is unit length. So these are the units of Kp, Kc and Kx. Thank you.